This lecture is going to cover periodic trends, and in particular ionization energy and electron affinity. So ionization energy is the amount of energy necessary to remove an electron from an atom. So remember, an electron is held to a nucleus because of the positive charge of the nucleus is attracting the negatively charged electron. So if we look at a hydrogen atom, for example, hydrogen has a single electron in the 1s orbital. And if we were to remove that electron, so we end up with a nucleus and just a free electron. It turns out it takes about 1,312 kilojoules per mole of energy to remove that electron from the atom and form the H plus cation. So we can look at some periodic trends as we look at ionization energies. So let's just walk through a couple examples of how we'd think through some ionization energy problems. And so for the first problem we have is explain why the first ionization energy, and what I mean by that is the energy it takes to remove the first electron from lithium. So lithium neutral goes to lithium plus an electron. Why does this amount of energy is 520 kilojoules per mole? But if you remove the second electron, so if we start with the lithium cation and remove another electron to form lithium 2 plus, this second ionization is 7,300 kilojoules per mole. So notice this huge difference in energy. Why does it take so much more energy to remove that second electron than the first electron? And with all of these ionization energies, what's really important is to think about the electron configuration of the atom or ion that's losing an electron. If we think about the neutral lithium, we have 1s2, 2s1, and lithium plus is 1s2. And so really what we're comparing is what electron are we losing? We are really comparing the loss of a 2s electron to that of a 1s electron. All right? And so it's much, much easier to remove the electron from the 2s orbital than it is the 1s orbital, because the 2s orbital is further from the nucleus, right? So 2s is further than the nucleus than the 1s. And second, we also know that the 2s is shielded from the nucleus by the 1s electrons. So the Z effective that holds on to that 2s electron is plus 3. But the 1s, that is plus 1. But the 1s electron feels the full nuclear charge of positive 3 of the lithium. So for both of those reasons, it's much harder to remove that 2s electron than the 1s. Another simpler way of stating this is it's always much easier to remove a valence electron than it is a core electron, right? That 1s electron is truly a core electron. So we can look at another table. Here we have some table of ionization energies, and these are the first ionization energies, second and third ionization energy of hydrogen, helium, and lithium. And so now we can ask ourselves why the first ionization energy of helium takes more energy than the first ionization of lithium. And again, what we're looking at here, so the first ionization energy is comparing these two numbers here, helium to lithium, first ionization. And again, we have to look at what is the electron configurations. And this is going to be very similar to the example we just went through. And what we're removing is, again, we're comparing the loss of a 2s electron in lithium to that of a 1s electron in helium. And what we see is, if you think about what Z effective holds the electrons, the lithium electron, Z effective, is plus 1, and the 1s electron feels a charge of a plus 2 from the nucleus. So it's going to be much harder to remove that helium electron because of the greater nuclear charge, and it's closer to the nucleus than the lithium. So the lithium electron being in a 2s orbital is going to make it much easier to remove than the helium electron in the 1s orbital. Why does the first ionization of helium require more energy than hydrogen? So now we're comparing 1s and 1s, and really the key here, the key here between hydrogen and helium, they're both 1s electrons. But now we have to consider the nuclear charge. The nuclear charge of hydrogen is +1. The nuclear charge of helium is +2. And so that greater nuclear charge makes helium-1 smaller than hydrogen, and it's going to attract those electrons more. They're closer to the nucleus. They feel a greater attraction of that charge, making it harder to remove that electron. So what we can start to do is look at some periodic trends. And so here's a nice plot of the ionization energy versus atomic number. So each red square is an element. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And so we can start to see some periodic trends. Again, this regular repeating patterns of a trend, this is this idea of why the periodic table was made. And so we see as you go down a group, right? As you go down a group, helium, neon, argon, right? Lithium, sodium, potassium, ionization energy is decreasing. So why does ionization energy decrease as you go down a group? It's because the electrons are getting further and further from the nucleus, making it easier to remove them because they're further from the nucleus. As you go left to right across a period, so lithium to neon, sodium to argon. So here's your second period. Here's your third period. Ionization energy is going up as you go across a period. So it goes up, 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 and then it drops to the third period. And it goes up, 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 and then drops to the fourth period. So what's happening here? What changes as you go from lithium to neon? Increased Z effective. Just like we saw with our atomic size, the increased Z effective +1, +2, +3, +4, +5, +6, +7, +8 make it much harder to remove the electron as you go from left to right. So it's a higher ionization energy. So down a group, we're adding a shell. The electron's further from the nucleus, easier to remove. Left to right, Z effective goes up, making the electron harder to remove. This is the same argument as we used for atomic size. We are seeing again, but now we're seeing it in terms of ionization energy. Now, as we look at this, one of the things we see is there's a couple of points that don't quite fit the trend. And so we see, I drew them out here, right here, and here, but we see the same thing in the second period going across. There's a couple of spots that don't seem to fit this ionization energy trend of increasing ionization energy as you go left to right. So we have to think about what's actually taking place here. And so we'll start off and let's think about what's going on right here. And to do this, we have to think about the ionization energy. So this dot, is beryllium, and this dot is boron. And so if we think about the electron configuration, we have 1s2, 2s2, and boron would be 1s2, 2s2, 2p1. And so what's actually taking place at this first drop is this difference between a 2s2 and 2p1. And remember, the order of orbital energy is the 2p electrons are higher in energy than the 2s. So by putting that next electron into the 2p, it's actually a little bit easier to remove this 2p electron than it is the 2s. Even though this has the greater Z effective, it's going to be easier to remove because it's higher in this subshell, right? And that's going to be the same argument that we see here, except in this case it's 3s2, 3p1, and here it's 2s2, 2p1. In our other spot, the other spot, we're looking at the difference between nitrogen and oxygen, and we see the same thing here, right? But phosphorus and sulfur there. And so we have to think about what's taking place in this location. And here we have to think about, again, electron configurations. We said this was 2p1, 2p2, so nitrogen's 2p3, and oxygen is 2p4. And so what we're actually seeing, here it is right now, nitrogen, 2s2, 2p1, 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 and then oxygen has 2p2. This is the first time, we see a spin paired electron. And so it's the difference between oxygen having a spin paired electron in the 2p's versus nitrogen, in which all the electrons are in different orbitals. And this spin pairing of electrons, two electrons in the same orbital, both of those electrons are negatively charged, so they're going to repel each other, raises the energy just a little, but it's just enough that it makes it slightly easier to remove the electron, even though it has the greater Z effective than for nitrogen. And so that's our ionization energy trends. The last trend we're going to kind of look at very, very quickly is what's known as electron affinity. And this is more or less the reverse of ionization energy. So electron affinity is the energy change associated with the addition of an electron to a gaseous atom. So in this case, we're adding an electron to form an anion, and we're seeing which atoms will release the most energy, right? So if we're adding an electron, it's going to release energy as we form a force of attraction. So which atoms are going to be best able? It's going to be the atoms with the highest Z effective that have a spot to hold the electrons. So which electrons are there? We can look at some charts that show this, but we'll kind of jump to the conclusions. The halogens, group 17, are the ones that are best able to grab an electron, right? And why is this? They have the highest Z effective of +7. The noble gases do have a Z effective of +8, but there's no empty spot for those electrons to go. So therefore, the easiest electrons to gain electrons are going to be the halogens, group 17, and then group 16, and so on, because they have high Z effective and they have a spot for the electrons to go. Thank you.